Welcome back to finite element analysis of solids and structures. Today, we'll finally deliver on the title subject of this course and talk about finite elements. So it was a long road to get here. And I'll start off by reflecting on how exactly did we get here. We've covered a lot of ground since we started this class. We started by discussing some of the underlying physics that motivated the description of how bodies move and deform under the application of externally applied forces. We utilized some fundamental assumptions, in particular, a continuum assumption of how we represented these structures by supposing that we could treat them as these smeared homogenized media that really could be regarded as being almost identical in how they appear at arbitrarily small length scales. And that enabled us to come up with these governing differential equations that explained how individual points in this particular structure had to satisfy equilibrium. So from that statement of equilibrium, this pointwise description of equilibrium in the format of a governing differential equation, we were able to formulate boundary value problems, which were problems that sought the solution for a particular displacement field or the displaced state of the structure under these applied loads. It had to satisfy this governing differential equation that we derived, and it also had to satisfy some additional boundary conditions that we imposed either on the displacement field itself or on whatever kind of external forces might be applied at the ends or on the boundary of this domain, subject to certain well-posedness conditions. But as it happened, these strong formulations of these boundary value problems weren't always so easy to solve. We could solve them in simple one-dimensional cases, but that was a limited opportunity for us to actually apply analytical techniques to solve those problems. In general, in more complicated 2D and 3D problems, it's not so straightforward. So we had to come up with some other way of expressing the same problem, just in a slightly different format, and that alternative format happened to be this corresponding weak formulation of the equivalent boundary value problem expressed in strong form. And the weak formulation was really nothing more than, you could think of it as a statement of virtual work in analog to a lot of classical principles in structural analysis. But the basic idea was that we could take this pointwise statement of equilibrium and convert it into this equivalent integral average form of equilibrium weighted by some additional test function or a virtual displacement function. And for any possible choice of this virtual displacement function, we should still satisfy this integral average weighted statement of equilibrium for any possible such function. And that was nonetheless an equivalent statement of this same boundary value problem, just reworked into this integral expression rather than as this differential equation as we had previously in the strong form. And finally, we said, well, even though we've expressed it differently, now in this sort of integral fashion, we've weakened some of the requirements of the solution fields that we're looking for, such that they don't necessarily have to be super smooth and continuous. They could be potentially discontinuous, at least in their derivatives. They still themselves have to be continuous functions for the displacement field in order to satisfy the fundamental requirements of compatibility. But their derivatives need not be everywhere defined. Now, that was a nice kind of additional thing that admitted a new class of functions that had possibly, not well-defined derivatives everywhere, and we'll take advantage of that fact momentarily. But even so, we're still restricted in terms of our ability to solve these problems because there's an infinite number of possible candidate solutions that we could try and test to evaluate whether they satisfy this statement of equilibrium, and an infinite number of possible displacement or virtual displacement functions that we could plug into this expression to try to evaluate and say, well, does it satisfy the weak form for this particular test function or this test function? There's an infinite number of such functions that we could plug in. So in order to make that problem more tractable, we had to take it one step further and finally come up with these so-called Galerkin approximations that said we're not going to test all possible functions in virtual displacement fields, and we're not going to consider all possible solutions for the displacement field. In fact, we're going to restrict attention and represent both our candidate solutions for the displacement field and for this virtual displacement field in terms of a finite set of functions, and construct these representations for the trial solution and for the virtual displacement functions as basically just a linear combination of these basis functions taken from some finite dimensional function space. A long walk to get here. But we're finally ready to talk about what can we do with these Galerkin approximations and how do we actually connect this to the concept of finite elements, which are a particular case of a Galerkin approximation, just choosing a particular set of basis functions, and we'll show exactly what those functions look like. Okay, so just to remind you of how we formulated these finite dimensional problems in the case of a Galerkin method, where we have these particular sets of basis functions, which I'm denoting as this kind of lowercase var phi symbol. There might be n of them, where n is some finite number of basis functions used to represent both the trial solution field and this virtual displacement field. If we took our statement of the weak formulation of equilibrium, which had to be satisfied for any possible candidate virtual displacement field V, then all we have to do is plug in these two expressions for U and V, expressed as these linear combinations of the basis functions. Plug them into these expressions, work things around. Notice that these expressions have to be satisfied for any possible choice of these arbitrarily selected virtual displacement coefficients. That's the V bar sub i's. So for any possible value of V bar sub I ranging from I equals 1 to n, these equations still have to be satisfied. We could exploit that realization to manipulate this equation a little bit further, rearrange some terms, factor out the summation over I equal 1 to n, and then make the argument that if V bar sub I is arbitrary, then the resulting expression that multiplies that particular V bar sub I has to be equal to 0 in summation. And from that argument, we came up with some finite number of equations, n equations in total, that effectively gave us this statement of equilibrium that had to be satisfied in this sort of weighted integral average sense, weighted by this particular corresponding basis function var phi sub I. All right, now that we had these n equations, we could take those equations and represent them as that kind of funny looking indexed kind of scheme, or we could convert them into an equivalent matrix vector format as a system of equations expressed in terms of the finite number of unknown displacement coefficients u bar sub I, ranging from I equals 1 to n. So a total number of n unknown displacement coefficients and a total number of n equations expressing the equilibrium of the system in this kind of weighted integral average sense. And from these, n equations and n unknowns, we can assemble them into this square symmetric system of equations. In the case of a symmetric Galerkin method, the resulting stiffness matrix will be a symmetric square matrix. And in general, assuming that the chosen set of basis functions are independent in the sense that you can't represent one of these basis functions as just a linear combination of the other basis functions. As long as that's true, and as long as you satisfy a few other requirements, then it is possible to invert this resulting stiffness matrix to actually solve for what the resulting set of unknown displacement coefficients are. Okay. Given that, and given that you can apply this method for any possible, choice of admissible independent basis functions used to represent our kind of both our trial solution and our virtual displacement functions, the question becomes, what particular set of basis functions should I choose in general if I'm solving a problem where I don't necessarily know ahead of time what the exact solution should look like? It might be nice and smooth It might have some kinks in it, but it still has to be continuous at the minimum. We have to search for solutions that will be continuous functions to satisfy compatibility. But beyond that, we don't really know what these functions should look like. They might be smooth. They might have some nice curvature to them. They might have some kinks. We just don't really know ahead of time. So really the question is, if we're going to formulate a general method for solving these structural analysis problems, we have to come up with a reasonable set of basis functions to use. And they should be, ideally, a convenient set of basis functions to choose, which also give us reasonable approximation properties. They should do a good job of approximating the representation of very general functions. So even if my function, maybe looks like very wavy and wiggly, or maybe if it has, other properties, I want to have a function, or really a set of basis functions, that does a reasonably good job of representing any possible function which might correspond to the exact solution. And having those capabilities, having a set of basis functions that does a reasonable job of approximating these possibly variable solutions, that's really the subject of many numerical discretization methods. The goal of many numerical methods is to try to come up with a better set of basis functions that better represents these kind of general solutions. But there's plenty that we could choose from. And in the last lecture, we took a particular look at this set of candidate basis functions consisting of just monomial functions, from which we can assemble general polynomial expressions to represent some arbitrary, function, which might kind of have some variations in curvature and things like that. But monomial functions, in general, they're nice and smooth. They have some other nice properties. And in fact, they have some nice approximation properties. As you increase the number of these monomial terms, as you increase the maximum power of these monomial terms and expand the number of functions that you consider, in the limit, as you kind of make that set of functions bigger and bigger, you actually do have some interesting properties that suggest that you will converge to the correct answer or the exact solution as you increase the number of functions and consider more and more of these monomial functions. So the monomial basis, and in fact in general, polynomial basis functions are actually a fairly good starting point. They have nice convergence properties in terms of their ability to approximate general solutions to these problems of interest, but they have some drawbacks. I won't go into all the details, but they do have some challenges. All right, other types of basis functions we might consider are the Fourier basis, basically just a collection of sine waves of variable frequencies. And sine and cosine approximations through Fourier basis functions are also very good starting points in their ability to exactly represent any possible continuous function. So they too are actually kind of a nice starting point, but they don't necessarily have a lot of utility in these particular problems where maybe if I really want to represent just like a constant, then actually have a hard time of representing just a constant function with a finite number of truncated Fourier basis functions. So they may be good for representing nice kind of like wavy signals in other kinds of domains, but in mechanics they're not always a great starting point, at least not for quasi-static problems. So really it comes to this. Is there some other set of basis functions that we might consider that aren't the monomial basis or the Fourier basis? What could this basis look like? Well, not to kind of build up and over-dramatize this, but the conclusion that we'll reach is that there is a set of basis functions which does a pretty good job and has a lot of other really nice properties, which I'll summarize later, but they are in fact what some people call the finite element basis functions. And these basis functions are really nothing more than a piecewise interpolatory set of basis functions that allow me to define these functions as basically a means of interpolating discrete values that I can kind of define through these particular points placed at different locations over the length of this structure. So finite element basis functions, as I said, they're particularly nice in terms of their ability to represent general functions. In general, though, they aren't always exactly smooth, as is the case and is evident from this particular example, where if I wanted to represent this somewhat general function using a low-order finite element set of basis functions, which basically give me piecewise linear interpolation of these discrete values, u1 through u5, corresponding to nothing more than the actual displacements at those specific locations, then you'll notice, even though things are constant over these individual subdomains, or the elements as it were, nonetheless you have these discontinuities or kinks in the representation of the solution field as you kind of traverse from one segment to the next. And that lack of smoothness could have been a problem if we were considering trying to solve the original strong formulation of the boundary value problem. But thanks to the fact that we've formulated everything in terms of this weak formulation, it's okay if the solution maybe has a derivative that's not particularly well defined at the specific nodal locations. So that's really, the workaround that we get from using the weak formulation. But these finite element basis functions, regardless of the fact that they're, a little bit discontinuous, nonetheless have also pretty good approximation properties, in the sense that, you can imagine, if I were to increase the number of nodes and elements discretizing this particular domain, putting in more nodes and more individual segments, according to the best approximation property of Galerkin methods, we anticipate that our ability to represent an arbitrary function will improve as we increase the number of elements. And that effective property of convergent behavior under refinement of this discretization into a finite number of elements is really what enables finite element methods to be very broadly applicable and helpful in solving general problems. Okay, but really it's nothing more than supposing that there's this particular set of basis functions corresponding to a finite element basis. However, we have yet to specifically define what these basis functions look like, and we'll get to that in a moment. But first of all, I want to define some of these quantities that I've already mentioned in the context of finite elements. So really, what do I mean by finite elements? We've kind of discussed this earlier in the class, but the idea is this. Supposing I have some structure, it's just a uniaxial member in this case of finite length. The idea of finite elements is to first take this structure and cut it up into a finite number of subsegments. And each one of these subsegments is terminated by some discrete nodal positions. So I define these discrete points in the domain, which terminate each one of these individual segments, and I call those discrete points nodes. In between these nodes, I define a finite number of elements. An element is really nothing more than some particular subdomain bounded by discrete nodes, as I've previously defined them. Then, over each one of these elements, I suppose that I can represent locally the solution for my general displacement field in terms of only the displacements at the nodes of interest for this particular element. So I suppose that each one of these individual nodes in the domain, these discrete points, 5 of them in this particular example, that each one of these nodes may displace independent of one another. And associated with each one of those nodes, I might assign a particular nodal displacement value. So in total, for this particular problem, if I have 5 nodes in total, then I say that I also have a total of 5 displacement degrees of freedom, or 5 displacement unknowns that I have to solve for. But over any particular element, say element 1, within that element, I have to say something about how the displacement field varies local to that element. And if I know that the displacement at the ends of this element, at its terminating nodes, have these discrete values, let's say u1 and u2 at nodes 1 and 2, then I have to also make some assumption about how the displacement field varies within the element itself. Now, you might not have thought of this up to now, but at the end of the day, if we don't really have any additional knowledge about how the displacement field should vary between these two node points, I really have to make some kind of guess. And at a minimum, whatever function that I choose to represent the solution local to this element, whatever I choose, it has to be a continuous function, and ideally it should pass through the nodal values themselves. If I'm being true about the representation of the solution as being this kind of representation of displacement at node 1 really should be the displacement evaluated at x equals 1. Same thing, the displacement at node 2 should be the value of the displacement field evaluated at x2. So to do that, I need to have a function that in some sense interpolates the values at the nodes within a given local element. And I can do this in one element. I can do it basically independently in all of the elements in this domain. And in the end, I can patch them all together to come up with some kind of general solution for the full variation of some solution field U over the full domain. But again, it has piecewise representation over each individual element. The question, though, becomes, assuming that I do take this course of action by saying that I want to interpolate the nodal values. And when I say interpolate, I really mean to construct a function that passes through those two discrete values at the endpoints or at the nodes of this particular element of interest. So for example, given, let's say, element 1 that has coordinates x1 and x2, the two nodal locations, and which has corresponding nodal displacement values u1 and u2. If I want to come up with some interpolating function that passes through those two displacement values, and which otherwise has maybe kind of some smooth continuous variation between them, then there's only so many functions that I could choose to actually represent such a function. In general, if I have two endpoints or two values representing the displacement at each of the two nodes, then I could choose to come up with some, let's say, linearly varying function, which can be expressible in terms of, let's say, a first order or linear polynomial, which itself has two unknown coefficients, a and b. And that correspondence between the number of these coefficients and representing some polynomial, a linear polynomial in this case, two coefficients to represent a linear polynomial, if I want to find out what those two coefficients should be, I can relate them actually directly to those two nodal displacement coefficients, u1 and u2, just by saying, well, I want to satisfy these interpolating properties. I want to ensure that whatever interpolation that I've chosen to represent the solution local to this element, as shown in this kind of equation in the middle of the screen here, I need to ensure that at least this function passes through these two values for u1 and u2 at x1 and x2. So effectively, I have these two unknown coefficients, a and b, representing this linear polynomial that I have to set, which also satisfy these two constraint conditions, expressing the interpolatory behavior of this local representation of the solution. So, two unknowns, two equations. I can then choose to simply assemble a system of equations representing exactly that set of constraints that I've imposed on what this function has to look like, with the unknowns that I have to solve for, a and b, arranged as a vector if you like, and that whole system of equations, just to be fun, can be assembled into this matrix system of equations. Small 2x2 system, which is easy enough to invert and solve for those resulting coefficients for a and b. And the resulting expression that I get for the corresponding variation of this linear function looks a little bit like this. And you can verify that if I were to plug into this expression different values for x, either x evaluated at x1 or x evaluated at x2, what I find is that I recover precisely these kind of constraints, that u at x1 gives back u1, and u evaluated at x2 gives back u2. So I satisfy my interpolatory conditions, and I construct a very simple straight line that just goes directly between those two values. So that's really the simplest way that you can rationalize how you come up with these interpolating functions, functions that pass through these discrete values assigned at discrete nodal locations. So with that, I could represent everything in terms of how I showed on the previous slide. I've kind of reproduced it here below this figure on the left, showing what the explicit representation for this function, as basically the function of the displacement field, is as a function of spatial coordinate x, where x is expressed in terms of the nodal positions also. However, as is commonly done in much of the literature, rather than representing everything in terms of spatial coordinates, or spatial coordinates as you would measure along the structure itself, it's more common to transform these different coordinates into a different coordinate system altogether, which involves shifting the coordinate x by some particular value, and also scaling it by a different value in order to transform the variation of this function expressed over the domain x ranging from x1 to x2 to instead ranging over some kind of local coordinate system expressed not in terms of x, but in terms of some other local coordinate, sometimes called xi, which is represented with this funny Greek character that looks kind of like a squiggly e. All right. Now, this definition of a local coordinate can be transformed given the representation for how the actual axial coordinate x varies along the length of a particular element, and expressed in terms of the specific nodal values of the n coordinates of this member. But in the end, it really kind of looks more like this. What I'd like to do is have an element local coordinate system that doesn't range from x ranging from x1 to x2, but has this element local coordinate psi, which ranges instead over -1 to +1. I could have defined the range differently, but canonically this is what's done in the literature. They define this local coordinate system for a particular element by transforming from element global coordinate x to this element local coordinate psi, and we suppose that we can define these sets of functions, these interpolating functions, in terms of the element local coordinate rather than in terms of the global coordinate x. All right, so within this element local coordinate system, I suppose that x1 is located at the coordinate psi equals -1, and node 2 is located at the coordinate psi equals +1. So at those two locations, I have to recover the condition that at psi equals -1, I recover u1, and at psi equals +1, I recover u2. And otherwise, I need to come up with this representation of the function u, not as a function of x, but in terms of the local coordinate psi. Okay, this is particularly convenient if you want to represent how the solution field varies in some element where you don't necessarily want the size of this element to really be controlled by, how big is this element in general. It's independent of size. In other words, you've normalized the domain of interest to be over -1 to +1. And there's some advantages to doing this, but we won't actually see and reap some of those advantages until we jump to 2D and 3D types of problems. All right, but for now, proceeding along these same lines, I can come up with a particular representation for u as a function of the local element coordinate psi, as shown in the figure below. So I have this representation of a constant, which actually happens to be equal to the average or arithmetic average of u1 and u2. So it's just u1 plus u2 divided by 2. That's the average value. Plus the difference of u2 minus u1 divided by 2 and then multiplied by the linear term of psi. And that actually gives me exactly this linear interpolation that represents u varying as a function of psi. Now I could manipulate this expression a little bit further, and instead of representing things in terms of a constant term plus this linear term that depends on psi, that's kind of trying to represent everything in terms of this set of monomial coefficients, in terms of psi being the kind of primary variable that might have different monomial powers and whatever. Instead, I could choose to manipulate things around and try to isolate these individual displacement values, u1 and u2, and find out what is the function that multiplies each one of those two nodal coefficients. Manipulating things around, I can come up with the expression shown below that has the same expression, just maneuvered around such that I have u1 multiplied by this first function, 1 minus psi divided by 2, plus the second coefficient, u2, multiplied by this other function, 1 plus psi divided by 2. And now that I have things manipulated into this format, you probably can kind of see things and where I'm going with this. But the idea is this. If I can choose to represent this function, u as a function of psi, in a format that looks kind of like u1 times some basis function, n1, plus u2 times another basis function, n2, then I can basically make the argument that local to this element, there are these sets of basis functions, which I'll call n1 and n2, which, at least in the local context of a particular element, can be called basis functions, but they also are sometimes called shape functions if I'm referring to them local to a particular element of interest. So I have two basis functions, n1 and n2, associated with node 1 and node 2, and which act in such a way that they enable me to interpolate the values of u1 and u2 at the endpoints of this particular element. It's also important to note that these shape functions are typically expressed in terms of the element local coordinate frame, in terms of this coordinate psi ranging from -1 to +1. So it's generally the case that when you're expressing shape functions, they are expressed local to one particular element as a means of interpolating nodal values and which range over this particular element local coordinate psi. Canonically, they take this particular form in the case of a simple two-noded linear element, where n1 is precisely 1 minus psi divided by 2, n2 is 1 plus psi divided by 2. And they also have this interesting property. If you were to graph them, kind of shown on the right, what you notice is that n1 actually has a value of 1 when you evaluate it at psi equals -1. So go ahead and plug in psi equals -1 into that expression, and you'll find actually that you'll get back that n1 equals 1 at psi equals -1. However, if you notice, if I plug in at psi equals +1, then n equals 0. And conversely, n2 is equal to 1 at psi equals +1, but it's equal to 0 at psi equals -1. So this kind of property, we'll see a little bit later, is precisely what enables these shape functions to be able to interpolate the specific nodal values u1 and u2 over this element locally. All right, so that's shape functions, at least in this kind of simple one-dimensional case. Now, each element will have its own set of local shape functions, expressed in terms of its own local element coordinate system. And we can do this to come up with these local sets of interpolating shape functions or basis functions that tell us how the solution should be interpolated between the distinct nodal values that terminate a given element. But it turns out that if we're being consistent about how all the elements are pieced together, then we can take these local shape functions defined on an element-by-element basis, and we can actually patch them together in order to come up with holistic representations of the basis functions in a whole domain ranging over the full size of the structure itself, consisting of all the elements stuck end on end. And what we'll find is that we'll get a set of basis functions, associated one for every single node in the structure, which give us a way of interpolating nodal values in this piecewise fashion. Now, you'll notice that these resulting basis functions are a little spiky. Sometimes they're also called hat functions because they kind of look like a little triangular party hat that you might wear at somebody's birthday party or something. But in any case, each of these different functions sort of looks like this triangular hat shape, It's certainly discontinuous, or at least its derivatives are discontinuous, because it doesn't necessarily have a well-defined derivative exactly at the nodal location, but never mind that. The idea here is that at least I can come up with some local basis function defined over the full structure itself, one for every node, and in particular, for node 3 in this example, the resulting basis function will look like this local kind of hat, but it will basically be, defined in such a way that this resulting basis function n3 associated with node 3 will have a value of 1 exactly at x3, and it'll have a 0 value at nodes x2 and x4, and in fact, it'll have 0 value anywhere that's not in, the elements directly connected to node 3. So those are some interesting observations and some nice properties that enable a few other interesting characteristics of finite element basis functions. But the main thing is that we can just kind of recognize that these basis functions are really constructed in this piecewise fashion. Over each element, we define these local shape functions, and the basis functions are really reserved as a terminology to say the shape functions put together and kind of stuck together in this global coordinate frame. All right, so to summarize some of the nice properties of finite element basis functions, the first property that's worth noting, and which we've already kind of asserted, is that finite element basis functions are interpolatory. That is to say, if we define some finite number of nodes, then basis functions as we've defined them through this finite element discretization ensure that whatever function we construct through this piecewise representation will directly pass through those specific nodal values for the displacement at each one of those nodes. So this interpolatory property is sometimes also called the Kronecker delta property, which is a property that says that each one of these nodal shape functions has to have a value of 1 when you evaluate that nodal basis function at the corresponding nodal location or nodal coordinate x, and at any other nodal location, that same basis function has to be equal to 0, which we observed previously. So the Kronecker delta property of these basis functions is essentially a corollary of this interpolatory property. The other property that's worth noting about these basis functions is that they satisfy a partition of unity, which is to say that if we were to take all of these different basis functions, these finite element basis functions, and sum them together over each individual element or, over the full domain of interest, what we'd find is that in a pointwise sense, the summation of all these different basis functions, they all sum to 1, which is another way of saying they form a partition of unity. And you can verify this for the case of these local shape functions defined over this particular element with the local coordinate xi ranging from -1 to +1. If we sum n1 and n2 together, considering their previously defined forms, what we find is that their summation is equal to 1. So, and that's true regardless of where you actually evaluate xi. So that's an interesting property, and in fact, that is exactly a consequence of this partition of unity property. There's some nice, consequences of this partition of unity property, but probably the most notable one is that you get a nice stiffness matrix that doesn't, appear to have like excessively large values in one portion of it and excessively small values in another portion of it. That's particularly important when you're trying to invert a stiffness matrix. If it has lopsided values, or in other words, a poor condition number, you can actually run into some issues when you numerically try to invert such a matrix. So the partition of unity property is really important for satisfying that extra condition, assuming that the basis functions are well proportioned and other things like that. All right, the last thing that's nice about these basis functions is they have something called compact support, which is, as I observed previously, that if you looked at any one of these different basis functions for a particular node, let's say, then you ensure that the value of the corresponding basis function associated with that node will only have non-zero value over the patch of elements to which that particular node is connected. And beyond those patches of particular elements to which that node is connected, beyond that, the corresponding basis function associated with that node will just be equal to 0. So you really only have to worry about, the value of this particular basis function being non-zero within the elements connected to the corresponding node that basis function is associated with. And the property of compact support becomes especially important when you're trying to ensure certain other beneficial properties of stiffness matrices. In particular, it's nice if you can ensure that your stiffness matrix isn't dense or isn't filled with values in every single entry and potentially very large stiffness matrix that you could potentially assemble. It becomes much more difficult to work with and invert stiffness matrices that have non-zero entries throughout the whole darn thing. It so happens though that if you have, let's say, a particular choice for your basis functions that satisfy this compact support property, then the consequence of that is that your resulting stiffness matrix won't necessarily have fully dense entries. You'll have a lot of zeros actually showing up in these arrays. And that can be really efficient and a source of great computational efficiency if you can leverage that fact. Or in other words, if you can leverage these sparsity properties of your stiffness matrix in order to avoid having to deal with all these potentially non-zero entries. All right, so that's finite element basis functions at a glance. We'll discuss more of the applications and the implications of using finite element basis functions, at least in the one-dimensional case, and we'll broaden our perspectives to the 2- and 3-dimensional analogs of these same basis functions in a later lecture. If you have questions, though, feel free to reach out, and I'll look forward to seeing you next time. All right, see ya.